Here we go. Hi, everyone. So 95 slides, 333 transitions in approximately 30 minutes-ish. So hi, my name is Red, but you know that already. In these 30 minutes or so, I'm going to give you enlightenment in 1 hour, 30 minutes-ish, or your money back. What I'm going to describe is at a top level is functional programming, which is kind of elephant-like. We're going to eat the elephant, and what you're going to get is not really going to look like an elephant, but you get the idea. So I'm just going to give you a rough view of the terrain and the advantages we get. All right, so hi. I'm I, 20 years of experience, obsessed with security, functional programming. I restore old keyboards and ants. By the way, the things behind me, that's my ants. I'll introduce you to them later if you're curious. So Mickey, why did we start with Mickey? Well, Mickey wasn't really a polecat, and he likes watching people play dominoes and fires, and he was killed in the line of duty, and he was in fact buried on the premises of the fire station with his tiny fire hat. Pull one out for Mickey. So why? Well, the year is 1936, and in 1936 there was a schism in the computing industry. On the one side, we had Alan Turing and his Turing machine. By the way, 1936 was also the year that the first commercial manufacture of magnetic tape occurred. So Turing machines being based on tape, probably a coincidence. But on the other side of the schism was Mr. Alonzo Church and Lambda calculus. They're two very, very different ways of solving computing problems. So let's talk. Let's start with an introduction to Lambda calculus, or not, because it's a really, really, really dry and painful subject. So instead, let's do something else. I want you to all reach for your mute buttons because I'm about to ask a question. Pop quiz. In 1965, there were how many programming languages? Let's hear some guesses.
5.
10.
15.
The
20.
25.
All right. Well, I'm sorry to inform you that at the time, there are in fact 1,700 programming languages.
What?
Exactly, in 1965. It's a little mind-blowing. Yeah. So, and those were almost all exclusively languages for Turing machines. On the opposite side, Lambda calculus, you pretty much had 3. You had Lisp, IPL, and APL. And why? Well, pragmatism. It's a lot easier to build and write in Turing machine programming in languages than it is in Lambda calculus. And I'm about to show you why. So first of all, let's talk about programming language paradigms. So imperative, which is what I'm sure most of us are used to, is here is a list of instructions. Please execute them in order. So, C, BASIC, SQL, JavaScript. Then you have the object-oriented, variations of it, such as Java, C++, and the JavaScript that still has an identity crisis. And then on the other side, you have more declarative languages, such as Haskell, Erlang, Elixir, Elm, Idris. And the theory behind that is, here's a list of things that I know are true, and I need you to work out what the answer is. And there's another subset called logical, which include languages like Absys and Prolog. And it's hard to really describe what they do, so I'll just show you a picture. I'm sure many of us in our time have done like this type of thing. That's the sort of thing that those languages are really good at solving, Prolog and Absys. It's for solving those types of problems. All right, so these things are always true. What does that mean? Well, on the one side, imperative. Let's play along. Okay, if x equals 1 and y equals x plus 1, and I say print y, what do we get? It's not a trick question, I promise. The answer is 2. Okay, functional. If x equals 1 and y equals x plus 1, and we say print y, what answer do we get? 2. See, they seem, pretty similar. Okay, all right. So let's do it this way. So imperative, if you do x equals 1 and x equals x plus 1, and you print x, what do you end up with? 2. Okay. In functional, if you say x equals 1 and x equals x plus 1, what do you get?
A linked
You get an
list.
explosion. Because there's no such thing as a number where x can be equal on both sides. In functional programming languages, that is not a command, that is an expression which is true. And it is not possible for there to be a value where x is equal to x plus 1, therefore it's illegal in the language. So why is this useful? Well, when you look at your code and you know the value of a variable cannot be changed, then you could do things like this. So this is a language called APL. The actual author of this won a Turing Prize for it. So in this example, and again, you guys can unmute and answer this for me. So in the first line, we assign the value of 42 to the variable a. And then the last line of the code prints the value of a. Would anyone like to take a bet looking at this code listing? What answer will be printed at the end of this program? What is the result? What does it print?
42?
Correct. Because a can never change, you could just do this. Come on, that's cool, right? How much easier does it make it? How much easier is your code to reason about when you do that, right? How much easier does that become? So for example, if you have and another advantage of having data that's immutable, can never change, is that if you have 1,000 threads performing operations on the same block of data, because the data is immutable, nothing can change, which means you never have to worry about the data changing. You never have to worry about any of the threads crashing and corrupting your data. You don't need any locks, mutexes, semaphores. It just works. And it makes your code scale a lot better because you guarantee things never change. You can scale it across CPUs, or you can scale it across machines, or you can scale it across data centers because you guarantee that data never changes. All right. So let's talk about this again. So these things are always true. It's another way of looking. Let's go back to imperative. Y equals x plus 1. If you put that in, any kind of imperative language, that will not compile. And the reason that it won't compile is because your compiler will say, I'm sorry, I don't know what x is, therefore I don't know what y is. Therefore, can you do something about that? Whereas in functional, that is completely legitimate. So it's legitimate. So then when we then set x equal to 1 and print y, you get 2. So functions are first-class citizens. So what we're actually doing there is we are, can you close the door on your way out, please? Thank you. So what that'll do is that function y equals x plus 1 is describing a relationship. So you're not describing what the value is, you're describing a relationship. And these functions are first-class citizens. So you can assign them to variables, you can put them in data structures, you can pass them to functions, you can return them to functions. They're just like anything else, a string or an integer or anything like that you'd used to be seeing in any other language. All right. So why is this useful? Well, we'll come back to that. So what the news does that mean if y equals x plus 1? Well, it means that since you have a relationship, you can actually draw up effectively a truth table, right? Which means that you always know that for the same input you get the same outputs, which means you can start to cache your results. These are pure functions. So it doesn't matter where it's executed, how many times you executed, what machine it's compiled on, what face of the moon, any of those things. If you have that guarantee, then if you've got a really expensive operation, right, a very hard thing, a very time-consuming thing, and you do it 100 times in your codes, you only ever have to calculate it once because you can guarantee that that will never change. If there's only one argument in this, this is called a monad. So the scary monad thing is actually really simple. It is a function that takes one argument. That's it. All right. So why is this useful? Why is the idea that when you have one input and one output and nothing else changes, how is that useful? Well, things we get for free. We can replace the hard thing with the lookup table. And it is, if you have one argument, it is literally a key value store, right? You never have to do the same calculation twice. Your compiler can actually look through your code and say, oh, okay, I see this expression is being used in multiple places. We're just going to execute it once, and we're going to substitute the result of that in all of these other places in code. And here's the fun bit. If the data is never actually used, then the code is never actually executed. The compiler can make that determination, and to the point where if you've got like 50 lines of code and it's doing all kinds of like mathematical stuff, if you can remember back in the day when you were in school, or maybe you do this in your day job where you're actually doing algebra and you're doing variable substitution and you're simplifying equations, your compiler will do that for you for your code. So these things are always true. What the news does it mean? Well, okay, let's take this a level above. Let's say you want to add 3 integers together. So to be clear, this is all going to be pseudocode. So please don't pick on the syntax. I'm making it up. Let's say you want to add 3 integers together, but you only have a function that sums 2 numbers together. Well, this is kind of what you'd expect to do, right? If you were a typical programmer, you'd sum 2 integers there, and then your total would be, you know, the sum of the previous 2 integers plus 1 more. Makes logical sense, right? Well, instead of doing it that way, remember, we can treat those functions as values, right? So not the result of the answer, but the actual calculation itself. So instead, let's define 3 functions like this. Like add1 takes one value, x, and returns x plus 1. Add2 takes a value, adds 2. Okay, you get the idea, pretty simple. So to add those 3 numbers together, you can just do that. Total equals add3, add 2, add 1, and give the first one a value of 0. Now, for anyone that hasn't been in this field, you're going to be like, why would you do this? Why are you overcomplicating it? Well, there's definitely a brick wall here, right? And I just want to tell you that this is the brick wall, which frankly, a lot of people like to consider setting up a wall against the rest of the world. And frankly, it's elitist. So I'm going to break down that wall and show you how this works, because when you see it, it's really, really, really simple. So back in the day, do you remember not knowing these terms? Encapsulation, class, property, method, object, inheritance, abstract, polymorphism, right? They were all things that, you know, before you started becoming a programmer, they were all terms that were like, I don't know what this means. Well, functional programming is just like that. It has its own vocabulary that seems intimidating. So by the end of this talk, I'm hoping that this will be as easy as shooting marine vertebrates in an abstract barrel proxy factory. Sorry, Java joke. So let's do this. So here are our 3 functions: add 1 function, add 2 function, and add 3. And so this is kind of how it works. So we're just, you know, replaying that. But again, let's take a let's give a real life application. Let's say we create a function that takes a cat and produces cat meat. And then we have a function called form dog that basically, you know, molds that cat meat into a dog form. And then we have a function which takes the molded cat meat dog form and then turns it into a hot dog. All right. So a hot dog is a cooked dog from a form dog with a grind cat, and you grind the cat. All right. So instead of writing it like that, which is really, really complicated to look at and very difficult to understand, we do these things, we write in pipes like this. So we'll say a hot dog is a cat, piped into our grind cat function, piped into our form dog function, piped into our cooked dog function. Now you can probably see why monads are interesting. Monads are really interesting because when you have one output, you can pipe it into a single input of your next function, which means your business logic and your application logic suddenly becomes really, really simple. All right. So let's talk about patterns and patterns in language. So this is, again, pseudocode. I'm sure many of us have written code like this before. So this function here takes a list of numbers, a list of integers, and doubles each number in the list and, you know, returns you a list of numbers out the outside. All right. So we've all seen this before. Wow. Looking really carefully at that item times 2, that looks like something that could be a function, right? So how about if we pull that out into another function? All right, this all looks logical, right? To those people who've done this stuff before, those people who write in imperative languages like C or JavaScript, this all makes sense so far. Well, what if we want to do a triple? Well, we could just create another one called a triple int function. So you see our double int list function and our triple int list function are identical, with the exception of, it's a call to a different function, either double int or triple int, depending on, whether you want to double the list or triple it. Wow, that's an awful lot of code. Do we think there might be any boilerplate code in there? Like maybe all of it? It is all boilerplate code, with the exception of that little function. Man, wouldn't it be so cool if you could pass a function as an argument to a function? Why? That's a great idea. Why don't we do that? Yeah, like maybe map. So map, the functional programming concept of map is you give map a list and a function to execute it, and you get a new list which contains all of the items of the list executed against that function. The other pattern is to execute a function on every item of a list, returning only a single value. For example, you might do that if you're summing numbers. That's a reduce. Or you may have a filter where you're saying, execute this function on all of these items in a list and only return the ones where it's true or where it's false, depending on, how you want to roll. Pretty cool, right? Very simple concept. So functional programming is all about lists. Function programming loves lists. So let's go back to our previous requirement. So we take our cat, we pipe it into a grinder, we form a dog, we cook the dog. How about we take another step back and instead we create a function which returns the function for the cat, that returns the function that makes the hot dog from the cat. Now we can take a list of cats, we can put it through map, and out the back we get a list of cooked hot dogs. See that? So for every item in the list of cats, it executes the hot dog function against the cat. So now we have this nice little factory. Well, we could take it a step further. We could take that map list of cats and we can create a factory which is a function which returns a function of a map of the list of cats, you get the idea. Now we've gone industrial, and we can just now generate as many of these as we want in parallel as we like. And this scales ridiculously. So this is clearly a stupid and immature example, which you'll hopefully not forget, because of course, as you can tell from my slides, I love me some cats. So let's talk about why this is useful. By going to the exact opposite direction. Those of you who have ever suffered with Java will probably recognize this book. It's the Gang of Four. It's the Book of Design Patterns. And to give you an idea of how this works, this book contains pages and pages and pages of all of these design patterns, which are meant to be common across all Java developers. They're meant to understand and apply these. Well, this is the functional programming approach I'm going to show on the right compared to how it works on the left. So for chain of responsibility, we replace that with a function. The command pattern, we replace with a function. The observer, we replace with a function. The state, we replace with a function. The interpreter, we replace with a function. Iterate. You get the ideas, right? The facade, the flyweight, the prototype, the singleton, it's functions all the way down. Functional programming is all about function composition. It's about getting everything into functions, composing them into what you want to do, and letting the compiler do its thing. So, like I said before, functional programming loves lists. Functional programming also loves infinite lists, or if we want to call infinite lists, maybe a stream. So that factory that we defined several slides back is all you need to process the same input to output at any scale. Because the exact same code, that original function we wrote, operates on a single item, it'll now operate on a batch of items, or will now operate on an infinite stream of items with the exact same code. It's pretty cool. All right. so let's, the other thing, if you remember, I said it was lazy. It only ever executed code that was needed. That means that what you actually consume at the input of your function is only consumed when you pull something from the back, from the output, right? So if you never use it, if you never print it, if you never do any of this, then none of the processing happens. And you know, from an ethical standpoint, remember I said data is immutable. That means that none of the cats in this example have been harmed by any of these factories because they all live forever. It's true. All right, so let's talk about the actor model. This is my favorite thing. All right, so concurrent is hard. Sorry, concurrency is hard. Getting things to happen and execute in the right order is hard. The actor model makes it easy. Well, by the way, Java has an actor model. JavaScript has an actor model. Lots of languages now have actor models. So let's talk about that too. All right, so firstly, don't panic. Because if you've ever used JavaScript, you've already used the actor model. You just don't necessarily realize it. So let's talk about it in one slide. So in the actor model, we have actors. Okay, and then we have mailboxes. And the rules are very simple. The actors do not share memory ever. The actors communicate only via mail. And you open mail, you do things, and you sleep. This is how it works. All right, so let me give you a production application. This is something that I wrote. It port scans the external perimeter of my company. It sends notification of changes. So let's quickly compare the design approaches. So from a non-active point of view, this is how you might do it, you know, using traditional methods. You run a port scan. You do like this if-then loop thing. You write the data to a database. So if it's been seen before, you update the time of the database. You have a separate job that scans for timestamps in the database, and then it notifies someone or deletes the item from the database depending on what it is. Well, the actor model makes it a lot easier. Let me show you. So we start by throwing random packets at the network. Just don't care, doesn't matter. Throw random packets at the network. We listen to all incoming traffic so that when they receive a packet, they send a message to our dedicated actor, that's a process, per IP or port combination. So this is how my application works. So we have two actors. One throws the random stuff, the other one listens. And then we have lots of actors which have those combinations and just passes messages like this. Let me show you how easy it is to encapsulate the logic in this. All right, business logic in 3 simple rules. If it receives a message, I'm born. That means send this is a new port notification to my subscribers, right? If it's first time it's existed, it's a new port. Send myself a message timed for 3 minutes in the future that says this port is closed. If I receive a message that says the port is open, then I cancel that timer and I reschedule it for another 3 minutes, right? Okay, I've skipped ahead. All right, so I send myself a timed message in the future that says the port is closed. Okay, if I receive a message that the port is closed, that means that it hasn't received another update, right? So it means that the port is closed and the process should die. So I'm looking for common code here, and you can see sending notification is in green, setting timers is in that nice orange color, which is making our designer friends' eyes bleed, and then white for content. All right, so I'm going to show you it in code. This is real code. This is real production code for my application. Yeah, so I'm born. I mean, just a function called init. Okay, this is new port notification to my subscribers. I just have a function that does that. Okay, that's what it looks like. Just notify subs. All right. And then send myself a time message for X minutes in the future that says the port is closed and set state. So in this example, it's 8 minutes. So set port close timer for 8 minutes, and then just store my state. That's it. That's all there is to it. So that's it. Okay, that's stage 1. Is that easy to reason about? Can you look at that code, not be a functional program, and understand what it's doing? So notify new port, so I'm notifying my subscribers, I'm setting a timer, and I'm just saving. Okay. So rule number 2, if I receive a message that says the port is open, all right, so you can see here, if I receive a message that is port open, cancel my scheduled timer, and send myself another timer for another 8 minutes, and then set my state. That's it. Is that easy to reason about? I think so. If I receive a message that says the port is closed, so again, the incoming message says closed port, I send a this port has been closed notification and die. That's it. Is that easy to reason about? So here's the thing. That is my entire application logic. To compare that to setting up a database, setting up a regular job to, look through your SQL tables to work out if things haven't been timed and all that kind of stuff. This is so much easier and clearer. So quick war story. I had a job requirements. I had 150,000 events per second coming in from RabbitMQ, which is a messaging engine middleware. All right. Event is encoded in Google protobufs, which is ASN.1 for not invented at Google. I had to do some filtering, like regular expressions, data manipulation. Basically, this was a logging engine, and I was, routing things to different syslog servers depending on the types of messages. Right. So my first design, receive the data from RabbitMQ. I decode the Google protobuf, and I send it to a round-robin data pool of the stuff that did all the regexes. And I did it this way because, in my mind, I was thinking the regexes and the logic were probably going to be the most expensive part. So I ran this, and its performance was setting one CPU on fire. So not good. Okay, try again. All right. So I received the data from RabbitMQ, and I send it to a pool of decoders, because at this point I'm thinking to myself, it must be Google protobuf decoding that must be eating all of my CPU. So I'm going to have a pool of those and a pool of regexes, and I'm just going to do that. And performance, it set all of my CPUs on fire. Have you ever been in a situation where you think that things are so bad that the only thing you can do is set the world on fire? And it's like, I'm just going to see how bad I can make this. So my third design. I have the actor receive the data from RabbitMQ, and I spawn a new process for every single message. So I'm now spawning 150,000 events per second. And each of those actors does all of the things I talked about before. And I'm thinking to myself, at 150,000 processes a second, this machine's going to set on fire. I'm going to go home and drink. No. It used 3% of CPU and 40 meg of memory. The competing design, the imperative design on a 16-core box was taking up 80% of all of the CPUs and almost 30 gig of memory. Rewriting it that way, I got 3% of CPU across all of them and 40 meg of memory. It was insane. And by the way, remember we were talking about things being immutable? This design scales across machines, across data centers without any modification to the code. None. Because it just works. I know nothing. So if I want you to take one thing away from this talk today, I want you to know that factional reactive programming, which is the new internet hotness, has been being done since the 1970s. So enjoy. Steps, find me on Discord. Choose a simple application to write. Try and use the functional facilities in your current language if you can, or if you're feeling particularly adventurous, and I recommend being adventurous, choose a new language to learn. The biggest impediment that you will find in this isn't learning the new language, because language is just syntax. It's going to be unlearning the way that you've been solving problems before. And that's going to take a little bit of a mind shift. And honestly, I'm here to help. If you want help with this, I'm more than happy to walk you through it. So Java, I'll mention it because there are some people here. Java 8 has formal support for functions in there. Scala is also a functional language which can compile to the JVM. Akka is the Java implementation of the Erlang actor model, poorly, but it's there. JavaScript. Actually, let's talk about Elm. So Erlang is a purely functional language that transpiles into JavaScript. It's actually really cool because if your code compiles, you are guaranteed, mathematically guaranteed with formal proofs that you will have 0 runtime errors. So the last point is if your code compiles, you're guaranteed 0 runtime errors. And for those at the back who might not have seen it, if your code compiles, you are guaranteed 0 runtime errors. Right. So Erlang and Elixir is my functional language of choice. It's mostly pure. It's not 100%. It's mostly there. It runs about 50% of the world's mobile telephony. It scaled WhatsApp to 2 million concurrent connections per server. That's not 2 million like connect, disconnect, disconnect, disconnect. That's actually 2 million concurrent TCP like concurrent sessions per server. And when they sold it, one of the founders of the company, who had his share of the $5 billion, he donated $1 million to the BSD Foundation and said, hey, can you all work on the parallelism, because your OS is the bottleneck, not the Erlang VM. Yeah, so 50 engineers for 900 million customers at the time of sale. That's not bad from a scaling point of view. F#, I'll touch on it. Microsoft's functional programming language. It's kind of like in the C#.NET space. Microsoft Research is heavily invested in it and is pushing it. They're actually pushing another language too, which is similar, whose name escapes me right now. Verona. Yeah, Verona, which is kind of a halfway house between functional and non-functional, but has a lot of the same concepts. So yeah, expect them to move in that direction. Haskell is perhaps the most famous one. It's an academic language designed for purity and research over pragmatism. It is an excellent language, but you are definitely going to hit the community. There's going to feel like a community wall there. But if you persist, they are nice people, I promise. It is possible with Haskell tooling to actually prove that your software is bug-free. I mean, like mathematically prove that you have no bugs. And it's type streams, but not as we know it. So I think that covers most of it. Do we have any questions? I have no idea how I did on time. Please do not be more than 30 minutes.
You're fine. What about Go and Rust?
That was
Go.
amazing.
So languages which are kind of, so they both have, so I know, okay, let me start with Rust. Rust definitely has some functional primitives. I'm aware of that. I would always recommend going for those types of things because I think it makes for cleaner code. I don't know too much about how it's actually implemented under the hood. I personally prefer staying as pure as possible because I think when you start to mix paradigms, it can get a little messy because people will tend to get lazy. And it's that laziness that introduces bugs. For example, so I mean, we all know the idea that you always have to pay the penalty, right? There will always be pain. The question is the pain going to be on you as the programmer, or is the pain going to be on your users? That is the fundamental question, right? So if you've got a language like Elm, which can be very difficult to get something to compile, although it's the friendliest compiler I've ever met. It's like if you change a variable, like if you change something and you need to change it in 2 places and you've only changed it to one, the Elm compiler will stop and it'll say, excuse me, I hate to bother you at this precise moment, but I was looking at the code that you presented to me and I was wondering if you might examine this line here and this line there, because there seems to be a difference between the two. Now, I'm pretty sure that you meant to add this argument here, but I would not presume to challenge your excellence. I mean, the Elm compiler is that verbose. It is a beauty to behold. And it is an example for all compiler authors, frankly. So yeah. Oh, another cool thing about Elm and the fact that it's immutable is that you can record all of your web development testing as a list of events and you can replay them. Because if you remember, everything is immutable, right? Nothing can change. So you apply you apply the event, apply the event, apply the event. You can run the same scenario 1,000 times, you'll always end up with the same answer. But they also have a time traveling debugger where you can like play 3/4 of the way through those events and you can be like, I don't like what happened there. You can rewind like, 16 or 17 events or however many. You can change the code, you can reload it, and then you can replay those events to see how your code change would change it. So it's really freaking cool in that regard. It makes development a lot of fun in that way.
This was so great, Red. Thank you. I love functional programming, but I don't get the opportunity to write it much. So like it's been fun to see that, you know, React is moving towards more functional components and everything, even though they still have effects and stuff. But this is very cool.
Okay, like I said, I'm happy if anyone is interested in going down this road. I am more than happy to help guide.
We may need to do like a functional programming book club type thing where like we each go and like, okay, this week we're going to build this small thing and like learn a language together or something.
That would be awesome. So I am a huge fan of being a language polyglot. So the best language, so people say, hey, what's the best language to learn? The best language to learn is the one that best solves the problem that you are trying to solve. Period, right? So there's always something you can learn from any language. The more languages you learn, the more different ways you see those languages try to solve those problems. Even if you don't use those languages, you can use the techniques that you learn in those languages to solve those problems in whatever language you are most comfortable in or your company is forcing you to use, if that makes sense. So you can learn different ways of solving problems. And that breadth is invaluable.
Does anybody have any more questions for Red?
One question, just a quick one. You possibly said this and I maybe overheard, but what language were you using for the example that you...
The example, both of the examples I used Erlang and Elixir.
Nice.
So I will tell you, so I write in Elixir and Elixir transpiles down to the same code that Erlang does, and it runs on the Erlang virtual machine. In a straight line, like if you have a single thread of execution, then the Beam, the Erlang virtual machine is not fast. Let me be clear. However, it can spawn millions of concurrent parallel processes inside its virtual machine and just execute their spread across however many CPUs or machines you have. So if you break your program up into like single function chunks and you're able to have them run in parallel because they're not dependent on each other, because you don't have side effects, if you can do that, then your scalability becomes effectively unlimited because you can just scale that out. The best example of that, of course, is a GPU, right?
Yeah.
So when you look at Moore's law and you look at the performance when you look at the performance of computers, we've hit the limit of how fast we can process, but we haven't hit the limit of how parallel we can go. And GPUs have scaled in performance incredibly over the last however many decades because each pixel is an individual thread of execution, right? The pixel here is not dependent on the outcome of the value of the pixel down here. So all of them can be executed in parallel. And so that's why that stuff has been able to scale. We need to move as programmers, as professionals, we need to move more into the mindset of getting our code to run in parallel. And the only way to really do that without having code run in parallel and have to wait because you're sharing memory, the only way to really do that is to use immutable data structures. And the cleanest way to do that, in my view, is to use functional programming.